This lecture is about the query likelihood probabilistic retrieval model. In this lecture, we continue the discussion of probabilistic retrieval model. In particular, we're going to talk about the query likelihood retrieval function. In the query likelihood retrieval model, our idea is to model how likely a user who likes a document would pose a particular query. So in this case, you can imagine if a user likes this particular document about the presidential campaign news, then we can assume the user would use this document as a basis to pose a query to try to retrieve this document. So we can imagine the user could use a process that works as follows, where we assume that the query is generated by sampling words from the document. So for example, a user might pick a word like presidential from this document and then use this as a query word. And then the user would pick another word like a campaign, and that would be the second query word. Now, this of course is an assumption that we have made about how a user would pose a query. Whether a user actually followed this process may be a different question, but this assumption has allowed us to formally characterize this conditional probability. And this allows us to also not rely on the big table that I showed you earlier to use empirical data to estimate this probability. And this is why we can use this idea to then further derive a retrieval function that we can implement with the programming language. So as you see, the assumption that we made here is each query word is independently sampled. And also each word is basically obtained from the document. So now let's see how this works exactly. Well, since we are computing the query likelihood, then the probability here is just the probability of this particular query, which is a sequence of words. And we make the assumption that each word is generated independently. So as a result, the probability of the query is just a product of the probability of each query word. Now, how do we compute the probability of each query word? Well, based on the assumption that a word is picked from the document that the user has in mind, then we know the probability of each word is just the relative frequency of the word in the document. So for example, the probability of presidential given the document would be just the count of presidential in the document divided by the total number of words in the document or document length. So with these assumptions, we now have actually a simple formula for retrieval, right? We can use this to rank our document. So does this model work? Let's take a look. Here are some example documents that you have seen before. Suppose now the query is presidential campaign, and we see the formula here on the top. So how do we score this document? Well, it's very simple, right? We just count how many times we have seen presidential, how many times we have seen campaign, etc. And we see here for D4, and we've seen presidential twice, so that's 2 over the length of document 4, multiplied by 1 over length of document 4 for the probability of campaign. And similarly, we can get probabilities for the other 2 documents. Now, if you look at these numbers or these formulas for scoring all these documents, it seems to make sense, because if we assume D3 and D4 have about the same length, then looks like we're going to rank D4 above D3, and which is above D2, right? And as we would expect, looks like it did capture the TF heuristic, and so this seems to work well. However, if we try a different query, like this one, presidential campaign update, then we might see a problem. What problem? Well, think about the update. Now, none of these documents has mentioned update. So according to our assumption that a user would pick a word from a document to generate the query, then the probability of obtaining a word like update would be what? Would be 0, right? So that causes a problem because it would cause all these documents to have a 0 probability of generating this query. Now, while it's fine to have a 0 probability for D2, which is non-relevant, it's not okay to have 0 for D3 and D4, because now we no longer can distinguish them. What's worse, we can't even distinguish them from D2, right? So that's obviously not desirable. Now, whenever we've had such a result, we should think about what has caused this problem. So we'll have to examine what assumptions have been made as we derive this ranking function. Now, if you examine those assumptions carefully, you will realize what has caused this problem, right? So take a moment to think about it. What do you think is the reason why update has 0 probability? And how do we fix it? Right? So if you think about this for a moment, you realize that that's because we have made an assumption that every query word must be drawn from the document in the user's mind. So in order to fix this, we have to assume that the user could have drawn a word not necessary from the document. So let's improve the model. Now the improvement here is to say that, well, instead of drawing a word from the document, let's imagine that the user would actually draw a word from a document model. So I show a model here. Here we assume that this document is generated using this unigram language model. Now, this model doesn't necessarily assign 0 probability for update. In fact, we can assume this model does not assign 0 probability for any word. Now, if we're thinking this way, then the generation process is a little bit different. Now the user has this model in mind instead of this particular document, although the model has to be estimated based on the document. So the user can again generate the query using a similar process, namely pick a word, for example, presidential, and another word, campaign. Now the difference is that this time we can also pick a word like update, even though update doesn't occur in the document, to potentially generate a query word like update, so that a query with update will only have 0 probabilities. So this would fix our problem. And it's also reasonable because we're now thinking of what the user is looking for in a more general way. That is a unigram language model instead of a fixed document. So how do we compute this query likelihood if we make this assumption? Well, it involves 2 steps, right? The first is to compute this model. And we call it document language model here. For example, I've shown 2 possible language models here, estimated based on 2 documents. And then given a query like a data mining algorithms, the second step would just compute the likelihood of this query. And by making independent assumptions, we could then have this probability as a product of the probability of each query word. Right? We do this for both documents, and then we can score these 2 documents and then rank them. So that's the basic idea of this query likelihood retrieval function. So more generally, then this ranking function would look like the following. Right, here we assume that the query has n words, w1 through wn, and then the scoring function, the ranking function, is the probability that we observe this query given that the user is thinking of this document. And this is assumed to be a product of probabilities of all individual words. And this is based on the independence assumption. Now, we actually often score the document for this query by using log of the query likelihood, as shown on the second line. Now, we do this to avoid having a lot of small probabilities being multiplied together. And this could cause underflow, and we might lose precision. By transforming the value with the logarithm function, we maintain the order of these documents, yet we can avoid the underflow problem. So if we take logarithm transformation, of course, the product would become a sum, as shown on the second line here. So it's a sum over all the query words, and inside the sum, the value is log of the probability of this word given by the document. And then we can further rewrite the sum into a different form. So in the first sum here, in this sum, we have it over all the query words, the n query words. And in this sum, we have a sum over all the possible words, but we put a count here of each word in the query. Essentially, we are only considering the words in the query, because if a word is not in the query, the count would be 0. So we are still considering only these n words, but we're using a different form, as if we were going to take a sum over all the words in the vocabulary. And of course, a word might occur multiple times in the query. That's why we have a count here. And then this part is log of the probability of the word given by the document language model. So you can see in this retrieval function, we actually know the count of the word in the query. So the only thing that we don't know is this document language model. Therefore, we have converted the retrieval problem into the problem of estimating this document language model, so that we can compute the probability of each query word given by this document. And different estimation methods here would lead to different ranking functions. And this is just like a different ways to place a document vector in the vector space would lead to a different ranking function in the vector space model. Here, different ways to estimate this document language model would lead to a different ranking function for query likelihood.